Hi, budding engineers. Welcome to Structure Engineering Lectures and welcome to a new playlist on the design of steel structures. In the today's class, we shall see the design of battened columns, right? Batten plates using bolted connections, the battening system as part of the design of built-up column, a numeric problem. In the previous class, we have seen the design of laced column in single lacing system like this, right? That was also a design of built-up column, right, wherein the sections, two channel sections are back to back. I hope you enjoyed the discussions there. If you really enjoyed the discussions, don't forget to click like, share, subscribe, comment to our YouTube channel, right? Now let us see. Uh, Before we see the actual discussion, let us see the brief profile of mine. I, Dr. D. Rupesh Kumar, obtained my BTech Civil Engineering from Nagarjuna University 1994 and MTech Structural Engineering from JNTU Hyderabad in 2000 and PhD Structural Engineering from JNTU Hyderabad in 2009. Presently, I am working as a professor of Department of Civil Engineering, University College of Engineering, Osman University, Hyderabad, Telangana State. I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching research at graduate, postgraduate levels. My research areas include reinforced cement concrete design, steel structural design, structural analysis, point element analysis, earthquake engineering, bridge engineering, and structural optimization. I published 45 research papers in international as well as national journals and conferences, and organized 3 international conferences and 11 national conferences and workshops, attended 43 workshops, visited 2 countries, delivered 13 guest lectures, and edited 2 books, supervising 14 PhD scholars and 30 ME theses. I'm a member of various professional bodies in India and technical committees for inspection. I've been actively involved in various consultancy works that are offered by the department and completed over 750 design proof checks and 150 designs of the RCC, steel, composite, low-rise, high-rise, multi-story buildings as well as road and rail bridges. Right now, once we see this student, let us see what we'll be discussing in today's class. This is how we'll be examining, right, the battened systems. Right now, what I am showing is this is a built-up column which is connected by means of the battening system in a steel building, right? Now this is also another schematic showing a hollow section connected by means of the battens, right, which are welded, right? This is of the battened plates or battening system. The schematic is now shown the same, right? This is what called the end batten, and this is what called the mid batten, right? Once again end batten, right? And the same is now shown in side view, and this is how these are connected to two channels back to back. Two channels facing each other like this. Two channels facing each other, wherein it is connected by means of a batten plate, right? Like this, right? A batten plate, right? This is the connection student, right? Now we'll examine this, and let us also see another schematic wherein this is already double laced and single laced along with the batten plates also, right? This is with cross members. However, code will not permit this type of design until as you prove that this is efficient enough, right? Or all the loads are taken by the different members. These designs we already examined in the previous video. This is how the single lacing design. This is what called double lacing. But now in today's class, what we will be designing is this battened column design. Right? These are the batten plate, right? Either it is intermediate or end batten, just to examine, right? Right? These are the other schematics which are showing the single lacing and double lacing and even single lacing, whereas these are connected by means of even batten plates, right? These are for the cross members, right? Now, once we examine this, let us move to the actual discussion student, right? Now that is how we'll now see first the design of battened built-up columns as per IS 800 2007, class 7.7, page number 50. All the Codal specifications pertaining to this battened columns. Now let me move to that page number 55, student, right, from IS 800. Yes, this is our battened columns from class 7.7 of IS 800 2007. I has attended 2007, page number 50, right? Therefore, now it says that the compression member is composed of two main members. Batten should preferably have individual members of the same cross section, right? Therefore, the cross section should not be different like this, right? The same cross section, right? And symmetrically disposed about their major axis like this, right? Disposed about the major axis. Where practicable, the compression member should have radius of gyration about the axis perpendicular to the plane of the batten, not less than the radius of the gyration about the axis parallel to the plane of the batten. That will see the during design means RYY shall not be less than RXX. Actually, the weak axis RYY for individual sections RYY vertical axis is the weak axis. Now for the battened or that of the laced sections, this is the condition that weak axis for individual section will become a strong axis for the built-up column, right? That is the advantage of this built-up columns, right? And the other Codal specifications, important Codal specifications are like this, student. The number of battens shall be such that the member is divided into not less than the three bays within the actual length from center to center of the connections, right? Now let me show this schematic, student, then you'll understand what do you mean by those three bays, right? Just now I have shown like this, right? Therefore now this column is seen with, right, 1 2 3 4 5 6 7 8 9 number of 10 bays are there, right? There is at least 3 1 2 3 3 battens should be provided so that we will have four number of bays, right? That is of the Codal specification, right? That is of the Codal specification, right? At least divided into not less than 3 bays. Therefore, this is of 1 bay. The center to center distance between the bay is given notated by capital C. Capital C from center to center distance between the bolted groups or welded connection as appropriate. Now, this is a battening system is now shown, and the same is also shown in plan, which are connected two channels facing each other, and this dotted line indicate a battening plate. If this line itself is thick line, student, then that is presumed to be a regular plate. If it is dotted, means that indicates that this is a battening plate which is connected by means of two rows of the bolts which are shown in elevation, right? Now this is a batten column section. And coming to the top, the designs, right? The effective slenderness ratio KL by R E for the battened column shall be 1.1 times KL by R naught, the maximum actual slenderness ratio of the column, to account for shear deformations, whereas this Codal specification for laced system is 1.05 times KL by R naught, right? There it is 5% more. Here for battened system it is 10% more, because even we do encounter the bending moments in this case. When batten plates are provided, even it will be subjected to bending moments also. Therefore additional 5% extra. Therefore 5 plus 5 10%, 1.1 times, right? And next one is the design of battens. How these should be designed, right? The batten shall be designed to carry the bending moment, just now I told, and shear forces arising from transverse shear force Vt equal to 2.5% of the total axial load or axial force in the entire compression member at any point in the length of the member, divided equally among between the two parallel planes of the battens. Generally here if I go to this schematic, I do have 1 and plus 1. There are two parallel planes. Therefore capital N is equal to 2. Therefore that is how. However, this force shall be divided equally among these parallel planes of the battens, right? And the battened member carrying calculated bending moment due to eccentricity of the axial load, calculated end moments and lateral loads parallel to the plane of the batten, shall be designed to carry actual shear force. Please make a note that we will see during design, in addition to the above shear force, right? And this main member shall also be checked for the same shear force and bending moment as for the batten. Now let us see what are those shear forces and bending moments, right? The battens shall be of plates, right? What are the sections? Now code says that either it may be plate or angle like this, or it may be a channel, or it may be an I section. And at their ends shall be riveted, right? They shall be riveted like this, right? They shall be provided by means of the rivets, right? Rivets like this, riveted or bolted or welded to the main components so as to resist simultaneously a shear force VB. A shear force VB is equal to VTC divided by NS, which is acting along the column axis in the vertical direction. VB will be acting in the vertical direction, and simultaneously is subjected to a bending moment, right? Like this, right? VTC divided by 2N, this much of bending moment in each direction, like this, subjected to a bending moment also. In addition to this vertical shear, VTC divided by NS, right, subjected to a bending moment also, like this, right? I'm just showing this, right? The deformed shape, right, where Vt is a transverse shear force as defined above, right, like this, right, and C is the distance between the center to center of the battens longitudinally by referring to this figure 11. Now we can see what is C is the center to center distance between the bolted groups, right, or riveted groups, or the welded group, right, and n is the number of parallel planes. Here in this figure it is capital N is equal to 2, and S is the minimum transverse distance between the centroids of the rivets or bolts group or that of the welding. That is how center to center of this riveted group to this riveted group, right, is what notated by capital S, right? These are the notations, right? Now next one, codal specification is that of the size, right? What should be the size, right? Now code says that when plates are used for battens, right? I'm just using these plates, right? The end battens and those at points where the member is stayed in its length shall have an effective depth. This effective depth, right? This is what effective depth longitudinally, the longitudinal direction not less than the perpendicular distance between the centroids of the main members, right? Now also for intermediate battens it shall have an effective depth not less than 3/4 of this distance, but in no case the effective depth of any batten be less than twice the width of one member, right? This width, right? Not less than this. That we'll see during the designs in the plane of the batten. However, the effective depth of the batten shall be taken as a longitudinal distance between the outermost rivets, right? And coming to that of the thickness of the battens, right? What should the thickness or that of the tie plates shall not be less than 1/50th of the distance between the innermost connecting lines of the rivets or bolts or welds perpendicular to the main members, right? Now let us move to the next model specification, student, right? Now next one is the spacing of battens, right? In this figure it is notated by capital C. What should the spacing of these battens, right? That is now given like this, right? The spacing of the batten center to center of its end fastenings, right? End fastenings shall be such that the slenderness ratio KL by R of any component over this distance shall neither be greater than 50 nor greater than 0.6 times the slenderness ratio of the member as a whole about the ZZ axis, right? Axis parallel to the battens, right? That is how the slenderness ratio shall be taken, right? Now coming to the welded connections where the tie or batten plates overlap the main members, the amount of the lap shall not be less than 4 times the thickness of the plate, right? 4 times the thickness of the plates. The length of the weld connecting each end of the batten plate to the member in aggregate shall not be less than half the depth of the batten plate, student. This is important, right? And at least 1/3 of the weld shall be placed at each end of the edge, right? And the length of the weld and depth of the batten plate shall be measured along the longitudinal axis of the main member, right? Now coming to the top, the next provision is next specification is compression members composed of two components back to back like this, right? Not facing each other, back to back like this, right? back to back, right? Back to back. In such case, compression member is composed of two angles like this, right? Two angles or channels or T's, right? T's back to back in contact are separated by small distance, right? As appropriate, right? This is how there is no gap between these two angles. Now, what I am showing is, right? Or there can also be a spacing in between these two, right? There can be a gap which is numerically equal to some numeric value, right? Therefore, in either of these cases shall be connected together by riveting, bolting, welding, so that the ratio of the most unfavorable slenderness ratio of the member between the intermediate connections is not greater than 40 or 0.6 times the most unfavorable ratio of the slenderness ratio of the strut as a whole, whichever is less, right? That is how this is how it should be designed, right? We'll see this during designs, right? With numeric problem, right? In no case shall the ends of the strut be connected together with less than 2 number of bolts. Please make a note. You cannot put just one bolt, even if it is required. You at least should put 2 number of bolts, students, right? And what should the diameter of these bolts is also given, right? The rivets, bolts, welds in these connections shall be sufficient to carry the shear force and movements, if any, specified for the batten struts. However, in no case the rivets or bolts shall be less than 16 mm diameter for members up to and including 10 mm thick. If the thickness is 10 mm, then the diameter should be 16 mm. If the thickness is more than 10 mm but less than 16 mm, the diameter should be 20 mm, right? And if the thickness is greater than 16 mm, then the diameter of the bolt or that of the rivet should be more than 22 mm. Please make a note. This we'll see during the designs, right? And that is how the various codal specifications pertaining to that of the battening systems or battened column designs, right? These are, I'm just giving these in nutshell, right? Therefore, IYY should not be less than IZZ, and the number of battens shall be such that the number of the members divided equally into not less than 3 base. Therefore, the slenderness ratio lambda should be such that 1.1 times scale by R, that of the original member, and transfer shear force VT is equal to 2.5 percentage, and the vertical shear force is equal to VT C divided by NS. These notations are already seen. The moment in this battening should be VT C divided by 2N, and the size coming to that of this size, the effective distance. Effective distance DC shall not be less than the perpendicular distance between the centroids of the main member, and the effective depth of this should not be less than 2 times the width of this flange of width of the member or width of the flange as appropriate, and thickness of this batten or that of this tie plate should not be less than 1 by 50th of the center to center distance between the between this main members, and the spacing shall be such that means C lambda B is equal to KL by R should not be greater than 50 or 0.7 times lambda C, right? For back to back battened connections, that is lambda, the spacing should be such that lambda should not be greater than 40 or not greater than 0.6 times the slenderness ratio. That also we have seen. And also, if the thickness is less than 10 mm, the diameter of the bolt should not be less than 16 mm. If the thickness is in between 10 to 16, then the diameter should be 16 mm. If the thickness is greater than 16 mm, the diameter should be 22 mm, right? And coming to the tough numeric problem now. I hope you understood the codal specification, student. Now let me move quickly to the top a design problem. In the previous case, we have seen a design of a lacing system. There also have designed a batten, which is referred to as a tie plate. However, in today's class, we shall see a totally battened column design, itself, right? Okay, student. Now let us see the design, right? Hence, now this is how the problem. Redesign the built-up column. What we have designed the other day, a single laced built-up column we have designed the other day. Now let us redesign the built-up column with 9 meter long to carry an axial force or compression force which is factored actually 1100 kilonewton with a length of 9 meters, right? The column is restrained in position and held in direction at both the ends, means it is hinged, right? And it is hinged it is hinged at both the ends, and it is provided with lateral connections systems as battens, right? You provide battening system. Lateral connecting system should be the batten, right? In the previous problem it was using a lacing, right? And also use bolted connections, right? Use Fe410 grade steel, Fe410 grade steel, right? That is the problem given, student. Now let us see what is the given data. Right? These are the given data, student. The factored compression load is equal to P is equal to C is 1100 kilonewton, and its length is 9 meter. However, the actual length is 9 meter. Therefore, if I go to this table 11, page number 45 of IS 800, let me go to that table 11, students, right? Table 11, page number 45. Page number 45. No, 45 is table 11, right? I am there in this table 11, wherein if both ends are hinged, if, right, you please see that, right? If both ends are hinged, now I do have, right, the effective length, right? Therefore, this is a translational, right? If both ends are hinged, right? Translational restraint, but at one end rotation free, at the other end also translation restraint, but other end free, right? Therefore, the effective length is equal to 1 times the actual length. Therefore, capital K, effective length factor, is equal to 1. Hence, substituting which, now we get the effective length itself is 9 meters or 9000 mm. However, now I want to fix a trial section. Therefore, in the previous problem, the trial section was fixed for a load carrying capacity of 1080. Therefore, what now I'll do is, even I'm fixing the same section, hence I'll move to that page number 143, wherein we have done the design of the trial section in detail there, right? Therefore, here now I have to have this trial section is now fixed. Let me see this, that loading, right? Here the loading given is 1100 kilonewton, student, right? Whereas for the present problem it is 1100, whereas for the previous problem it was 1080, right? That is how the only difference, right? Hence, if I see this, right, difference, let me see this, right? Here I do have, yes, I do have, I'm assuming the FCD, the design compressive stress, as 152 Newton per mm square, 150 Newton per mm square, right? Or let me go to this, how I am fixing that 152 Newton per mm square, right? Let me go to this page number 143, right? 143. Therefore, there I am arriving at this trial section, right? Trial section as like this, wherein this is how that design of built-up column with the lacing, right? There I am assuming slenderness ratio lambda is equal to 70, right? Whereas that was subjected to 1080 kilonewton. Here it is 1100, hardly 20 kilonewton more. Therefore, keeping in with the experience, I am assuming the slenderness ratio as 70. Therefore, if I go to this table 44 of table 10 of page 44, right? Let me go to that table page number 44. Let me go to that 44, right? I am there in that page number 44. From this, now I have to have the effective length. Effective length is already 1. That is already taken care. Therefore, and even coming to the top, this channel is the buckling class C. Therefore, now I'll go to this table 9C. Wherein from page number 42, right? Let me go to this page number 42, student, right? Therefore, that is how this channel is the buckling class C. About any this channel is buckling class C. Therefore, from this page number 42, let me go to this back page number 42. Yes, I'm there in page number 42 for that buckling class C. For lambda is equal to 70, for that standard ratio lambda is equal to 70, and for Fi is equal to 250. 250, I do have the design compressive stress as 152. Therefore, once I know this design compressive stress, therefore this value is noted. The area required is equal to 1100 divided by 152. 1100 divided by 152. Now it works out, say, a value uh, approximately 7237, right? Therefore, that is how. However, for trial section, I'll increase this area by 25 to 50 percentage. 25 to 50 percentage. Now I am increasing by 25 percentage, student, right? Therefore, that 7236 multiplied by 25 percentage. Now it is working out roughly 9000 9046 mm square. Therefore, now for each of these section, 9046 divided by 2. Therefore, it now works out approximately 4523 mm square. Say approximately 4500 mm square, right? I'm just increasing the area by 25 percentage, but as a student, you please increase this by 50 percentage. Because I want to optimize the section, I am proceeding with 25%. If it fails, I'll increase by, say, 35%. Even if it fails, now I'll increase by 50%, right? Therefore, I want to optimize the section. Hence, I want to choose a section from SP61 1964 table 2. Right? Let me go to this table 2, page number 6, student, from SP 61, which is Structural Engineers Handbook 1, table 2, page number 6. ISMC 300, right? That is how ISMC 300, right? Therefore, for which the properties, right? What I require is 4523 mm square. Therefore, however, this is now having 4564 mm square. Therefore, it is just okay. Right? Therefore, ISMC 300 at a unit weight of 35.8 kg per meter, having this much of area, 4564 mm square, and the depth of the section and the width of the flange 90 mm, right? Other relevant properties I'll note down, right? And the thickness of the flange, right? Thickness of the flange and the thickness of the web, right? Thickness of the flange is 13.6 and thickness of the web is equal to 7.6. Now, what is important for us is the radius of gyration, Rxx and Ryy. Therefore, this is a Rxx is equal to 11.81 centimeter, means 111.8, and Ryy is equal to 2.61 centimeter, 26.1 mm. Therefore, I have just noted down all these relevant properties, students, right? This is how all the properties are noted from Structural Engineers Handbook 1. And also the moment of inertia about the strong axis is equal to, right, IZZ or IXX is equal to 6362.6 10 to the power 4 mm to the power 4, and about the weak axis, about that vertical weak axis is 310.8 10 to the power 4 mm to the power 4. However, we have provided two such channels. Therefore, the area provided is equal to 2 multiplied by 4564 is equal to 9128 mm square, which is greater than 9046 mm, 9046 for this case mm square. Therefore, it is okay. However, once I fix the trial section, student, now let me see the next. I need to fix the section. However, the maximum slenderness ratio in this case is for this battened built-up section should be 1.1 times scale by R. Now I'll go to that. Before that, what I'll do is I'll also fix it. Once this section is okay, let me check what is that slenderness ratio. Let me check this slenderness ratio, right? Now just bear for a moment, right? Therefore, now I'll go to this section wherein I am I am now fixing that section as ISMC 300 student, right? Wherein now the slenderness ratio as per this IS 800 2007 class 7.7.1.4 1.4 page number 51. Just now we have seen that page number 51, right? Page number 51, right? Page number 51. This is how, as per this we do have this slenderness ratio shall be 1.1 times KL by R naught, right? That just now we have examined. Therefore, I'm just recalling that same 1.1 times this length is 9000 divided by 118.1. Please make a note, right? Because RXX is equal to 118.1 and RYY was some around 23.6. However, please make a note that for built-up section, the design is such that RYY for the built-up section shall not be less than RXX. Means for the built-up section, RYY is greater than RXX. Means for the built-up section, IYY is greater than IXX. Hence, if that is the case, hence for the built-up section, because it is placed symmetrically about this major axis, hence RXX will be 118.1, which is the minimum value. However, RYY for the built-up section is greater than 118.1. That is our target as per the Codal specification. Hence, for the built-up section, R min is equal to 118.1. That will decide later. Hence, you now target for the slenderness ratio, right, of 83.83. However, from this table 9C, page number 42. Let me go to this table 42, student, right? Of IS 800, right? 42 means yes, 56, yes, right? Therefore, from this now I do have what is the slenderness ratio, right? What now I got? This slenderness ratio is 83.83. Hence, now I'll note down for Fy is equal to 250. For 80, I do have FCD value is equal to 136, and for slenderness ratio lambda 90 is equal to 121. Therefore, for in between, I need to interpolate. Therefore, I'm just interpolating that. For slenderness ratio 80, FCD is equal to 136. For slenderness ratio 90, FCD is equal to 121. Therefore, for slenderness ratio of 83.3, it is how much? It is 136 minus 121 over a difference of 10 multiplied by over 3.83. It is how much? It works out, say, 130.26 odd value, or approximately 130.27 upon interpolation, right? Therefore, once I get this FCD value, now what I'll do? Now I'll also do is that whether this slenderness ratio, what I got 83.33, whether what I got this 83.33, is it okay? Yes, let me check, right? Therefore, however, if I go to this class 7.8.1, page number 52, let me go to that page number 52, student, right? And then in page number 42, therefore 52, and then in that page number 52. However, I am using a compression member composed of two components, two channels back to back, right? Please make a note. I am using two channels back to back. Therefore, for which the member between the intermediate connections shall not be greater than 40 or 0.6 times the most unfavorable slenderness ratio of the strut as a whole, whichever is minimum. Therefore, I just noted that, and as per that, lambda should not be greater than 40 or should not be greater than 0.6 times slenderness ratio of the compound or built-up section. 0.6 multiplied by 83.83. Just now we have calculated that. Therefore, it works out 50.29. However, out of this 40 and 50.29, 40 will govern, whichever is minimum. However, my slenderness ratio 83.83 is much greater than the this slenderness ratio should not be greater than 40, right? Now, therefore, this 40 is okay, right, for individual section 40, whereas for the compound section it is 83.83. Therefore, 40 is okay, right? Now, coming to the top, this spacing, the spacing should be such that, right, the spacing should be such that now before I go to the spacing, student, what now I'll do that I'll fix the spacing between the two channels, right? Therefore, before I go to the spacing of the lacing system, before I start this, let me go to this spacing between the two uh, uh, two channels, right? Now, therefore, once the section is now okay, now what I'll do is that I'll say, as per the Codal specification, as per the Codal specification, the spacing between these two channels is notated by mm. Therefore, as per the code, just now we have seen that IYY should not be less than IZZ. Therefore, that indicates that IZZ is nothing but two that of the two channel sections, 2 multiplied by IZZ of the each channel is equal to 2 multiplied by IYY of that of the each channel plus area of each channel multiplied by S by 2 plus CYY, this H square. H is now S by 2 plus CYY whole square, right? Therefore, that is how the Codal specification, right? Therefore, once I see this, where S is the back-to-back distance between the two channel sections in mm, right? Between the these two channel sections, right? Then we know the numeric values for this, right? Numeric values for this, because this is given in page number 196, right? Therefore, now substituting which, I know what is IZZ. 2 multiplied by 6362.6 10 to the power 4 is equal to 2 multiplied by IYY of the each channel is equal to 310.8 10 to the power 4 plus area of each channel is equal to 4564 plus S by 2 23.6 whole square. Solving which, now you will get the spacing between the channels is equal to 183.2 or say 183.5, right? Or not less than. If you put less than this one, then IYY is less than IXX, which is not acceptable by the code. Therefore, it should be not less than. Therefore, once I do this, now let me go to the let us fix the spacing. Let us fix the spacing between these channels, as say, just now I got this 183 point odd value, but now I want to provide a spacing of 200 mm, because even for the 200 mm directly from SP61 I can note down what are the relevant properties for the built-up channels, two channels placed back to back, right? That is how I'll fix the spacing between the channels as 200 mm, right? Therefore, that is how the trial section along with the spacing between the channels is now over. Now what I'll do is that I'll now fix the spacing of these battens, right? Spacing of these battens. Therefore, I want to initiate the design of the battens, right? These designs of the battens is the next subheading. However, these battens should be spaced at a distance of c mm distance apart, right? Therefore, what should be the spacing, right? If I go to this class 7.7.3 page number 51 of IS attended student, right? 51, right? Now I do have, as I'm there in that, right? The code says that as per this Codal specification, student, right? The spacing should not be greater than 50 or 0.7 times the slenderness ratio of the main member, right? Therefore, now with respect to this Codal specification, student, right? This one, right? Spacing of the battens as per this 7.32, right? KL by R of any component over that distance shall neither be greater than 50 nor greater than 0.7 times the slenderness ratio of the member as a whole about major axis, ZZ axis. Therefore, substituting the numeric values, now I'll get lambda is not greater than 70 or 0.7 multiplied by slenderness ratio. Just now we got 80 point odd value, 8. sorry, this value is equal to 83.3. Therefore, substituting which 83.3 multiplied by 0.7, it works out say 58.68. Out of these two, whichever is minimum. Therefore, lambda should not be greater than 50. Lambda should not be greater than 50. That is how you now you fix the spacing between these battens. C is only unknown, right? Therefore, C should not be greater than 50 multiplied by RYY. RYY of that of the radius of gyration of each channel section about the weak axis, that is already known, which is 26.1. Therefore, it works out not greater than 1305 mm or say 1300 mm. However, it will be fixed from practical point of view, because now I do have this length as 9 meter. Therefore, if I say 9 meter divided by 9000 divided by 1300 mm, I will be getting 6.9. Therefore, that is not acceptable. Therefore, R says 7. Therefore, I'll say like this. Therefore, now I'll get some 1286. Is the practically it is feasible. Therefore, that is how I can fix the actual distance, right, as the 1287. That I'll show, right. Now, next one is that of the once we fix the spacing between the batten student, next subheading is what should the size of this batten plate? What should the size of the batten plate? I do have the end battens like this, right? These are the end battens, right? End batten here as well as at the bottom end batten, and these are the intermediate battens, 1, 2, 3, so on and so forth, right? Therefore, this is the end batten, right? Therefore, what should the size of this end batten, right? That now will fix, right? Hence, if I go to this class 7.7.2.3 of page number 51, now what the code says. Let me go to this page number 51, student, right? Page number 51. Yes, I'm there in that page number 51. Now what the code says is that the size, right, its a length shall have an effective depth longitudinal and not less than perpendicular distance between the centroids of the main members. That we already seen. However, for the intermediate battens, it shall have an effective depth of not less than 3/4 of this distance, but in no case less than the effective depth of the batten be less than twice the width of these one member in the plane of the batten. The effective depth of the end battens shall be taken as the longitudinal distance between these outermost bolts, as well as the thickness of the batten should not be less than 1/50th of the distance between the innermost connecting rivets, right? Therefore, once we have already examined that Codal specification, should now substitute into the formula or formulae, right? Therefore, for the end batten, right, this D depth of this effective depth of this end batten should not be less than 200. 200 is the spacing between the two channels, plus 2 multiplied by cy, right? That is equal to 23.6, right? 23.6. Therefore, it now works out say not less than 247.2. And even other Codal specification is that it should be greater than 2 times the width of this flange, which is 90 mm. 2 multiplied by 90 is 180. Therefore, it is 247 is greater than 180. Therefore, it is okay. Means 247.2 is okay. Let us say if I get to 147.2, which is less than 180, it is not acceptable. Therefore, in such case, you fix 180, not 147.2, student. Please make a note of, right? It is okay now. Hence, D is equal to 247.2 is okay. And coming to the top, the effective depth, that of the intermediate batten should be like this, that it is 3/4 of this distance what we got, right? 3/4 of 3/4 multiplied by 247.2. It now works out 185.4, right? Now, also coming to the top, the thickness, right? The code says, just now we have seen that the thickness should not be less than 1/50th of 200 plus that bolts will be provided at a distance of 50 mm. Therefore, that 50 here and another 50 at the other end. Therefore, that now works out, right? Say 300. 300 divided by 50 means 6 mm, right? Therefore, the thickness of this batten plate should not be less than 6 mm, right? And coming to the top, the edge distance from class 10.2.4, page number 74. Let me go to the page number 74. Page number 74. 74. Yes. Now the code says that from this specification, I do have sorry, this page number 74. 74. Yes. Right. Now I do have this distance. This distance. Just wait for a moment, right? This distance. The end distance from this class 10.2.4 should not be less than 1.5 times the diameter of the hole, as well as the pitch, right? Minimum pitch should not be less than 2.5 times the nominal diameter, as well as the maximum pitch for the compression member should not be more than 12 times the thickness of this member or that of the 200 mm, whichever is minimum, right? This is how the specifications, as well as the other specifications are that if I use a diameter of the bolt, what should the hole diameter, right? Generally we'll be using 16 to 22, therefore 2 mm more for the hole diameter, right? Once we examine these Codal specifications, student, now let us see. Therefore, now end distance is equal to 1.5 multiplied by, I am assuming the diameter of the bolt as 16 mm, therefore it now works out 27, but not less than, or say 35 mm. Therefore, once I fix the edge distance, the overall depth is equal to this effective depth plus one edge distance here, as well as one edge distance at the bottom. Therefore, that now works out 2 times edge distance plus 70. Therefore, 247.2 plus 70, it works out, say, 317, or say approximately 320 for the end plate. For the end batten plate, it is 320, and thickness should not be less than 6 mm. And for this length of this end batten is 200 plus 2 multiplied by 90, right? 380, right? Hence, provide. Now I am saying that this end batten, what should the size? Should be 380 mm length and 320 mm depth, overall depth, with a thickness of 6 mm, right? 380 by 320 by 6 mm. I'll show that schematically also, student. Once I do that, similarly now I'll initiate the size of the intermediate batten. Just now we have seen that the effective depth of the intermediate batten should not be less than 3/4 of this 247.2, means 185.4, which is greater than 180 mm. It is okay. Therefore, the overall depth should be 185.4 plus 2 edge distances plus 70, or say 255.4, or say 260 mm. Hence provide the intermediate batten of size 380 mm length and 280 mm overall depth with a thickness of 6 mm as shown in the figure. Now I'll show those figures also, right? Once this is how the figures, right? That is how for the end plate I am using 380 mm, right? 380 mm, right? And a depth of 320 mm and a thickness of 6 mm, right? Now next, that is how the end plate. Similarly, you see for the intermediate plate also, right? Now next, once I fix this, let me go to the design. Just now I fixed it. To start with, I have fixed the sections, right? Whether this section can bear the vertical shear and as well as the longitudinal shear or not. That now we'll check, right? Therefore, now for which now I need to calculate those design forces, right? Now I'm doing that, right? And so the next heading is the design forces, right? Design tension in the batten as per this class 7.7.2.1, page number 51. Let me go to this page number 51, right? Let me go to this page number 51. Yes, 51. Therefore, just now we have seen that the batten shall also resist simultaneously a shear of VB is equal to VTC divided by NS, and also a moment M is equal to VTC divided by 2N. Therefore, now I am recalling this formula. Therefore, VT and also from the same page, it should resist 2.5% of the total axial force. Vt is equal to 2.5%. Hence, substituting with, now I'll get say Vt, the transverse shear. Transverse means in the horizontal direction, right? Acting in the long horizontal direction for the entire column, right? 2.5 multiplied by 1100 kilonewton, that works out say 27.5. acting horizontally. However, I do have two end batten plates, right? Two end batten plates like this, right? One on positive plane, one on the negative plane. Hence, capital N is equal to 2. Therefore, the and also just now I told that how many number of spacings are required. However, 9 meter is the distance between the ends of these columns. Therefore, that divided by, actually I got 1305. Therefore, if I divide, now I get 6.89. But I already told that it should the nearest highest integer 7, right? 7. Therefore, the exact spacing is 9000 divided by n, 7. 1286, right? Let me show this, right? This exact spacing is 1286, student, right? Here, this center to this center is 1286, or this is 1286. This is 1286, right? 1286, right? Here to here, right? 1286, right? Once I get this exact spacing, now what I'll do is with this exact spacing only I'll calculate what is that longitudinal shear VB. Longitudinal shear VB is equal to VT C divided by NS. However, now I already know these numeric values. VT is already 27.5 kilonewton, which is to be resisted by two batten plates, and the spacing between these batten plates is 1286 divided by S. The spacing is 300 mm between these channels. I'm sorry. Where S is let me go to this IS 800, student, right? Where S is the minimum transverse distance between the centroids of the rivets of the groups. That is already this 200 mm, right? Means this, right? This clear distance is 200 mm plus 50 plus 50. Therefore, it is 300 mm, right? Therefore, that is how it is 300 mm. This is 300 mm. This, yes, right? Therefore, substituting with, now I get 58.94 kilonewton. Actually, this shear force is acting in the longitudinal direction of the column. Therefore, it is acting in the vertical direction. Actually, it is a shearing force for this plate, right? For this plate. Now, also the bending moment, right? Simultaneously, this batten plate is subjected to a bending moment of VTC divided by 2n. Therefore, substituting the values, now I have 27.5 multiplied by 1286 divided by 2 multiplied by n. 2 batten plates we are using, that divided by 10 to power 6. Therefore, it works out say 8.84 kilonewton meter, because all these inputs are in terms of Newton mm. I have divided with 10 to power 6. However, sorry, this 27.5 is in terms of kilonewton, student. Therefore, I am dividing with 10 to power 3 so that I'll get kilonewton meter. 8.84 kilonewton meter. I'm sorry, 27.5 is already in terms of kilonewtons. Therefore, once I get this bending moment, I just got the design forces. Then what now I'll do is in the next subheading I'll check for the stresses. After getting these design forces, the next step, check for the stresses. Hence, first let me check whether this end batten, which was already provided as 380 by 320 with a thickness of 6 mm, can resist this much of longitudinal shear as well as the bending moment or not, right? Now, please see this. That since this VT transverse shear is only 27.5 kilonewton only on this batten plate, whereas that vertical shear VB is equal to 58.294. Therefore, out of these two, right, 58.94 is more compared to that of this horizontal 27.5 kilonewton. Therefore, this VB, which is acting in the vertical direction of the column, will govern the design. Hence, now I'll check for this shear, for that shear only. Hence, the actual shear stress, shear stress due to this direct shear that is causing the direct shear, as well as this due to bending also I do have the shear force, right? Now there is a direct shear stress is equal to Fs, notated by Fs is equal to direct shear force 58.94 divided by the shearing area is only 320 depth over a thickness of 6 mm. Please make a note. 320 is the depth of overall depth of this end batten plate. That works out say a numeric value of 30.69, which is much less than the permissible shear stress as per this class 800 2007 class 10.3.3, page number 75. Page number 75. Let me go to the page number 75, student, right? Page number 75. 75. Yet. Actually, that is for the bolted connections. Also, that is also applicable for the normal section steel plate also. Actually, that is how the nominal shear stress is equal to Fu divided by root 3. However, the design shear stress is equal to Fu divided by root 3 divided by partial safety factor. Therefore, I'm just recalling this. I'm just substituting here. Hence, 250 divided by root 3 is the nominal shear stress. That divided by design means 250 is with a factor of safety with 1.1. For 250, the factor of safety is 1.1. Therefore, it now works out say 131.2. However, I just got direct shear stress as 30.69, which is much less than 131.2. Hence, it is okay. There is a first check, right? And simultaneously, this end batten plate is also subjected to a bending moment of 8.84 kilonewton over a length over a width of 320 mm with a thickness of 6 mm. You just please see, right? That is how it is bending. Therefore, if I cut a section at any given section, this movement is resisted by 320 mm depth BD square, right? D is equal to 320 and over a thickness of 6 mm. Therefore, BD square by 6. Therefore, B is equal to 6 mm divided by D, 320 whole square, that divided by 6. Therefore, M divided by Z. Therefore, the actual bending stress FB is equal to M by Z. It now works out 86.33 MPa. 86.33 MPa, but as per this IS 800 2007 class 7.1.2.1, page number 34, the permissible, let me go to the page number 34, student, right? Just back of a moment, 34, yes, right? Now the code says that this is actually the reference of the direct design compressive stress or direct compressive stress FCD should be less than or equal to Fi divided by gamma m naught, right? However, the same is also applicable here, right? Because we are there in the compression member. Hence, this in any case not less than 250 divided by Fy 1.1. And also, if I go to the designs of the beams, there also the permissible bending stress is equal to Fi divided by gamma m naught. That is also same 250 divided by 1.1, which is 227.27. However, I got the actual bending stress as 86.33, which is much less than 227.27. Therefore, it is okay. However, please make a note that compared to that of the bending stress value of 83.66, this shear stress is very small, 30.7. Means primarily this flat is governed by the bending. Means more bending stress is there compared to that of the shear stress, right? However, because this is under the action of both bending stress as well as bending stress, right, which is causing the shear as well as the direct shear also. Hence, direct shear also. Now I'll check for the combined stresses also later, right? Now let me check the individual check first for the intermediate batten, right? Intermediate batten, whereas its size is 380 divided by 260 divided by 6. Therefore, the actual shear stress as explained in the previous case, is equal to 58.94 10 to the power 3 divided by 260 multiplied by 6, it works out say 37.78, which is much less than the permissible shear stress of 131.2, and as well as the actual bending stress is equal to 8.84 10 to the power 6 divided by BD square. B is 6 multiplied by 260 whole square divided by 6. That works out say 130.77, which is much less than the permissible bending stress of 227.27 MPa. It is okay, right? Therefore, these are okay in the individual checks. I'll also do the combined check also, right? Before I do that, let me also fix the bolted connections, means how many number of bolts are required, right? And you please make a note that the thickness of this channel section TF from the SP61 is 13.6, but however, as per this class 7.8.4, page number 52, right? Let me go to this page number 52. Just wait for a moment. Page number 52, student, right? 52. Yes, this is the page number 52. 13.6 is just greater than 10 mm and less than 16 mm. Therefore, it is in between these. Therefore, 20 mm diameter bolt must be used. 20 mm diameter bolt must be used. Therefore, it is just greater than 10 mm and this 13.6 is less than 16 mm. Therefore, diameter of the bolt should be 20 mm as applicable to these designs, right? And just now we have seen that as per this table 19, already explained in the previous discussion, that diameter of the hole is 2 mm extra. Therefore, it is 22 mm. And if I go to this IS 1367 part 3 2002, page number 9, student, right? The net area of this along the threaded zone, right? Threaded area, otherwise, right? Of this 20 mm diameter bolt, right, is given. Let me just go revisit this. I am there in IS 1367 part 3 2002, and for M20 it is 245. 245 is a net net area of this bolt, or if you don't remember that, you can approximately if you don't have an access to that code, you remember this formula as 0.78 multiplied by pi by 4 d square 30 square. Therefore, 0.78 multiplied by 314, it works out same 245 mm square is the net area of this bolt of 20 mm dia, right? Hence, if I go to this class 10.3.3 page number 75, let me go to that page number 75, student, right? 75, right? 75, yeah. Therefore, there I do have these shear capacity of this bolt VDSB is equal to VNSB divided by gamma MB, where VNSB is equal to FU divided by root 3 NN multiplied by AN. Similarly, for the bearing capacity of the bolt, VDPB is equal to VNPB divided by gamma MB, where VNPB is equal to nominal bearing strength of the bolt given by 2.5 kb dt FU, where kb is the list of the 4 values: E divided by 3 d0 second value, P divided by 3 d0 minus 0.25 third value, FUB divided by FU, and fourth value is 1. Therefore, once I note down these, now let me substitute into the formula as per this, right? Therefore, the design capacity of this bolt is in single shear. Please make a note that here the channel is connected to the batten. Therefore, this is only one single plane. This is only one single shear plane where it can fail. Therefore, n, the number of shear planes is equal to 1. Therefore, that nn is equal to 1 multiplied by the 245 multiplied by nominal shear stress of the bolt is equal to 400 divided by root 3. That divided by 1.25. It works out say 45.26 kilonewton. For 20 mm diameter, you please remember this as 45.26 in single shear. Similarly, if I go to this Codal specification, now I need to fix what is KB. Therefore, now I am saying that KB is equal to E divided by 3d naught. which is equal to 33 divided by 3 multiplied by 22, assuming E is equal to 33. However, we already fixed it as 30, 35. Even then also it is approximately 0.5, right? The second one is pitch, P divided by 3d naught minus 0.25. However, the pitch, just now we have seen in the previous specification that 2.5 times nominal diameter, 20 mm. 2.5 multiplied by 20 is equal to 50. Therefore, assuming 50 divided by 3 multiplied by 22 minus 0.25, it is around, it is 0.5. Third one is FUB divided by FU is equal to 0.975. Fourth one is 1. Out of all these, right, 0.5 is the minimum value. 0.5 is the minimum value. Therefore, KB is equal to 0.5. Hence, substituting that, now I'll get the bearing capacity or bearing strength of the bolt is given by 2.5 multiplied by KB, 0.5 multiplied by diameter of the bolt, 20 multiplied by the thickness for the bearing. Please make a note that I do have the thickness for the bearing is I am choosing a batten plate of 6 mm, whereas the flange thickness itself is 13.6. Therefore, after these two, the 6 mm batten plate will fail first, not that of the 13.6 of the channel section, student. Please make a note. Therefore, the thickness for the bearing is that of the flat, that of this batten, which is 6 mm. Therefore, substituting which, now I'll get that multiplied by 400 divided by 1.25, that would 10 to the power 3. It works out say 48 kilonewton. Therefore, the bolt value is the least of these two, 45.26 or 48. Therefore, 45.26 is the least value. Hence, the number of bolts required is equal to, I do have a vertical shear of 58.94 divided by bolt value 45.26. Therefore, now I'll get roughly 1.3. But just now already we have seen in the Codal specification as per this class 7.8.2, page number 52, that the number of bolts in any case not less than 2. Please make a note of, right? However, now I'll say R say 3 number of bolts. Because the depth is more, almost say roughly 320 mm. Therefore, I'll say R say 3, or even you may say more also. If more is the depth, even you can say more number of bolts. It is material, right? Therefore, I'm using 3 number of bolts for connection, right? Therefore, if I'm using 3 number of bolts, what is the actual pitch, student, right? Therefore, now the pitch works out 320 minus 2 edge distances as 2 multiplied by 35 divided by 2. Therefore, my pitch is fixed as 125, whereas as per this class 10.2.2, page number 73, minimum pitch should be 2.5 multiplied by the nominal diameter 20 mm or say 50 mm. Therefore, now it is 125 is greater than 25 mm. Therefore, it is okay. Similarly, for the what is the pitch for the intermediate battens? For the intermediate battens is pitch is equal to 260, because the depth of that intermediate batten is 260 minus 2 edge distances, 2 multiplied by 35 divided by 2. Therefore, for intermediate battens, that pitch is equal to 95. Therefore, this is how for the end battens that pitch worked out 125 and 125, and this is that edge distance 35, right? Therefore, we have fixed the number of bolts as a 3 as well as the edge distances as well as pitch, right? Now, once I do this, now what I'll do is I'll also do a combined check. This is the last check, right? Therefore, check for the combined shear stress, right? Because it is subjected to that in the bolts, right? Please make a note, because 3 number of bolts are there. Therefore, the direct shear stress in the each bolt, because 3 bolts are there, is equal to that vertical shear is equal to 58.94 resisted by 3 number of bolts is equal to 19.65 kilonewton. However, also you please see that this is subjected to a bending. This batten plate is subjected to a bending moment of 8.84, but code says that even their connections should also be designed for that much of bending moment. Please make a note of. Therefore, now I'll say that these are also subjected to a bending moment of 8.84. Therefore, here you please see that the bolts are there. in the plane of the bending like this. Therefore, this is how type 1 bracket connection. Akin to that of the type 1 bracket connection, what we have discussed in the previous class, student, please revisit what do you mean by type 1 bracket connection and in detail the designs there. I'm just skipping off for want of time. Therefore, the type 1 bracket connections. Therefore, there we have seen it is these bolts are subjected to a shear due to bending moment, which is given by mr divided by r square. Therefore, I have to have the extreme bolt is at a distance of 125 mm, right? That is how r1 and r2, right, both are at the same distances. Therefore, this extreme bolt is subjected to not only the vertical shear in the vertical direction, but also the horizontal shear due to bending. Therefore, this extreme bolt is under a shear of 19.65 kN due to vertical shear as well as horizontal shear due to bending, which is now given by mr divided by sigma r square. Therefore, that is numerically equal to 8.84 10 to the power 6 multiplied by extreme bolt is at a distance of 125 divided by 2 bolts are there, r1 at the top and r2 at the bottom, right? 2 multiplied by 125 whole square, that divided by 10 to the power 3. Therefore, now that is subjected to a shear force of 35.36 kilonewton in the horizontal direction, in addition to vertical shear of 19.65. Therefore, the resultant of these two is square root of this vertical shear of 19.65 whole square plus this horizontal shear of 35.36 whole square. Therefore, the combined shear stress is equal to 40.45 kilonewton. However, as per the code, the maximum force which can be resisted by the bolt is the bolt value, which is 45.26 for this 20 mm. Therefore, this combined shear of 40.45 is just less than 45.26 kilonewton. Therefore, these bolt designs are also okay. Because I want to propose the bolt designs, and I am saying that yes, these are also taking the not only the shear force, vertical shear force, but also they are designed for a bending moment. Please make a note. Not only we have designed these batten plates for vertical shear and bending moment, student, but also we have designed these bolts for vertical shear as well as the bending moments. Their connections also as per the code, right? That is how the design of a battened plates like this, right? Therefore, that batten plate I am showing. However, this batten plate is using the welds, right? Let me show this, right? That batten is like this, right? That batten plate is like this, right? As shown in this figure, right? These are the battens what I have provided at the end, right? That is of the design, student. I hope you understood the discussions what we had in today's class. Therefore, if you have really enjoyed the discussions what we had in today's class, don't forget to subscribe, like, comment and share to our YouTube channel. We'll meet in the next class with the design of splice as well as the effective length of the column members. Till then, bye bye, students.